Hello everyone, welcome to MK Academic Solutions. So in this video, I am going to explain you chemical equilibrium. This is lecture number 4. So topics covered here: factors influencing on equilibrium constant and applications of equilibrium constant. So these two already I have explained you in the previous video. So now in this video I am going to explain you factors influencing on the equilibrium constant and also applications of equilibrium constant. Okay. So now let us see first factors. Which factors influence on the equilibrium constant? Okay. Now just come here. Okay. So factors influencing on the equilibrium constant. The first factor is stoichiometric representation. Stoichiometric representation of same reaction. Stoichiometric representation of same reaction, same chemical reaction, same chemical reaction. Okay. So here same chemical reaction we are going to represent by using different stoichiometric coefficients. Then that time equilibrium constant also going to be changed. See here, the first one 2SO3 gives rise to SO2 plus O2. So for this just consider equilibrium constant is K1, and here the same reaction SO3 is gives rise to SO2 plus O2. So now this is the K2. So now here what is the relation between K1 and K2? Okay. So simply here first write the equilibrium constant K1. See here K1. So K1, how we can write K1? K1 SO2 square O2 power 1 by SO3 square. And whereas K2, how we can write K2? K2 is equal to SO2 into O2 power 1 by 2 by SO3. Okay. So this is the K2. So now how we can relate the K1 and K2? So now now here what I will do here, SO2 square and O2 power 1, and here O2 power is there. Now what I will do? I will do square in both side. So let us consider this is the second one and this is the first one. So now I am going to take the first one. Okay, first one only you consider, or else the second one you consider. Square the second equation both side. Okay, square. Do square equation number 2 in both side. So when I will do square in both side, what I will get? So here K2 square equal to, so here SO2 is there, SO2 whole square we will get, and here O2 power is there, O2 power 1 by 2 whole power 2 we will get by SO3 whole square we will get. Okay. Therefore K2 square is equal to, so this term when you observe very carefully, this total value is nothing but what? K1. This total value is nothing but what? K1. Therefore we can write it as the K1. So therefore K2 square is equal to K1. Therefore K2 is equal to square root of K1, or else we can write it as the K2 is equal to K1 power 1 by 2. 1 by 2. So now here what is the relation between K2 and K1 means K2 is equal to K1 power 1 by 2. Okay. So here this is the process. To prove this, this is the process. Simply here by seeing the equations only we can give the relation. See here it is the equation number 1 and it is the equation number 2. So now how we are getting the equation number 2? Equation number 2 by simply dividing. What we are doing? We are simply dividing the equation number 1 to get the equation number 2. With which number we are dividing? With or simply we are multiplying with 1 by 2 or dividing with 2. So here this multiplied number goes to the numerator, to the old equilibrium constant. Okay. So now simply how we can write this one? Say for example A is gives rise to B, and here the equation number 1 I am going to multiply with n. So here n moles of A is gives rise to n moles of B. Equation number 2 it is. Okay, it is equation number 1 and equation number 2 you consider. So here equilibrium constant is K1 and here equilibrium constant is K2. So now what is the relation between K1 and K2? Simply how we are getting this second equation? By multiplying the first equation with n value. That multiplied value will goes to the numerator. Therefore K2 is equal to K1 power n. K2 is equal to K1 power n. Okay, and you take some generalized example also. For example, two Hi is gives rise to H2 plus I2. H2 plus I2. Okay, and Hi is gives rise to half H2 plus I2, half I2. Okay. So now it is the K1 and here it is the K2. So now what is the relation between K1 and K2? So here K1 is the equilibrium constant 1, K2 is the equilibrium constant 2. So therefore here K2. How we are getting this second equation from the first equation? By dividing with 2 or multiplying with 1 by 2. Therefore K2 is equal to K1 power 1 by 2. Next you take some more examples also, no problem. 2NH3 is gives rise to N2 plus 3H2. For this equilibrium constant is K1, and the same reaction I am going to take by changing with the stoichiometric coefficient. Means I am going to multiply with some particular number. So with which number I am going to do? Multiply with 1 by 3, means 2 by 3 NH3, 2 by 3 NH3 is gives rise to 1 by 3 N2 plus H2. This is consider it as the K2. So now what is the relation between K1 and K2 here? Here relation is K2 is equal to, how we are getting the same reaction only, but what I changed children? Stoichiometric coefficients. Means what I have done here, I multiplied with 1 by 3. Okay, therefore K2 is equal to K1 power 1 by 3. K2 is equal to K1 power 1 by 3, or else simply here K2 is equal to square cube root of K1. Like that you can write. Okay, this is the relation. Now I will give an example. You need to write the relation between the two. So I am going to take PCl5 is gives rise to PCl3 plus Cl2. So you consider it as the equilibrium constant K1, and now what I am going to do? 2 PCl5 is gives rise to 2PCl3 plus 2Cl2. This is the K1, right? Sorry, it is the K2. Now what is the K2 is equal to? K2 is equal to what? So now you write the relation between the K1 and K2. So now you can take for the practice, right? Next one, mode of representing the equation. Mode of representing same reaction, mode of representing the same chemical change, same chemical reaction only we are going to represent in different manner. Means here we are not going to change the stoichiometric coefficient. Here what we are going to do, we are going to inverse. What we are going to do, we are going to inverse the reactions. See, for example, N2 plus O2 is gives rise to 2NO2. So now here what are the reactants? N2 and O2 are the reactants and 2NO2 is the product. So for this you can consider it as the equilibrium constant is K1. So the same change only, but what I am doing now, I am making now NO2 is the reactant, N2 and O2 are what? Products. Okay, clear? So now for this what I am going to consider K2. So now here what is the relation between K2 and K1 means? So now we can prove also this relation. First you write the K1. Okay, you write the K1. So when you write the K1 is equal to what you will get? NO2 whole square by N2 power 1 and O2 power 1, and you write the K2. So K2 you write. Okay, so now K2 is equal to what? N2 power 1 and O2 power 1 by NO2 square. Okay, so this is the K2. So now what I will do, I will divide. What I will do now, I will take this as the equation number 1 and this as the equation number 2. So now in both side what I will do, 1 by K2 I will take, means I will inverse. Here K2 is there now, 1 by K2 I am making, here K2 by 1, or I am just inversing 1 by K2. So when I inverse, this also will become reverse, 1 by K2. 1 by K2 is equal to, 1 by K2 is equal to NO2 square by N2 power 1 and O2 power 1. So it is nothing but what, children? It is nothing but what? See here, this is only we got. So therefore 1 by K2 is equal to K1, or K2 is equal to 1 by K1. Okay, so now here what we understood here, if you inverse the same chemical reaction without changing any stoichiometric coefficient, so what will happen? The new equilibrium constant is what? So here this is the new equilibrium constant is equal to 1 by of old equilibrium constant, means the old equilibrium constant will come in the denominator. Simply what you remember here, when you inverse the reaction, the new equilibrium constant is equal to 1 by old equilibrium constant. So when we inverse the chemical reaction, and when you inverse the chemical reaction, new equilibrium constant is equal to 1 by of inverse, or simply you take the inverse of old equilibrium. Okay, equal to inverse of old equilibrium, equal to inverse inverse of old equilibrium. Old equilibrium. Okay, this is the statement you can remember. So when you, this is the mode of writing equation, means simply if you inverse the chemical reaction, the equilibrium constant also going to be inverse. Okay, so now based on this statement, let us have some practice. Let us take here some examples. Simply I am taking the hypothetical example. A moles of A plus B moles of B is gives rise to C moles of C plus D moles of D. So now here let us assume for this equilibrium constant is K1, and the same reaction, now reactants I am making as the product I am making as the reactant. C moles of C plus D moles of D is gives rise to A moles of A plus B moles of B. So now here it is the K2. Therefore, what is the relation between K1 and K2 here? Therefore, here K2 is equal to 1 by K1, or simply K2 is equal to K inverse. K2 is equal to K1 inverse. So this is the relation between what? Old equilibrium constant and new equilibrium constant when you inverse. Now let us use the combination of first condition and second condition. Means what I am going to do, I am going to inverse the reaction and also I am going to change the stoichiometric coefficients. So, okay, right. See for example, A is gives rise to B. Very simple example I am going to take. A is gives rise to B. Okay, this is the, let us consider it is the reaction one, equilibrium constant is K1. Next to 2B is gives rise to 2A. This is the equilibrium constant K2, equilibrium constant K2 here. So now here what is the relation between K1 and K2? So simply here K2 is equal to what? 1 by K1, but here simply not inverted, and also stoichiometric coefficients also changed. How stoichiometric coefficients are changed? See here, stoichiometric coefficient 1 is there, and here stoichiometric coefficient 2 is there, means it is multiplied with 2. So therefore K2 is equal to 1 by K1 square. The multiplied value goes to the power value and it is inverted, that's why equilibrium constant is also going to be inverted. Therefore K2 is equal to 1 by K1 square, or simply K2 is equal to K1 power minus 2. Like this also you can write. So this is about what? Stoichiometric coefficient and mode of representing the chemical equation. Next, the third factor, that is when, the third one is when addition of two equilibrium leads to another equilibrium, the product of their equilibrium constants give the equilibrium constant of the resultant equilibrium. Okay, simply just we understand this one by taking the example. So let us consider A is gives rise to B. So this is complete reaction. You consider it is occurring in different intermediate equilibriums. Okay, so first initially A is converting into C, and C is converting into D, and D is converting into B. Okay, so when you add all these equations, you will get this resultant equilibrium. Okay, so now good, when addition of two equilibriums, or two more than two equilibriums, two or more than two equilibriums leads to another equilibrium, leads to this another equilibrium, the product of their equilibrium constants. So the product means multiplication we will do. The product of these all equilibrium constant K1, K2 and K3 is equal to what? Equilibrium constant of the resultant equilibrium, equilibrium constant of the resultant equilibrium. Okay, now let us come here, this reaction. N2 plus O2 is gives rise to 2NO. For this equilibrium constant is K1, and next to 2NO plus O2. 2NO plus O2 is gives rise to 2NO2. So this is the K2. Now when you add these two equations, what you will get? N2 plus 2O2 is gives rise to 2NO2. So this is the resultant one. How we are getting this equilibrium? How we are getting this equilibrium reaction? By adding of equation 1 and equation 2. Okay, means when you get the new equilibrium by adding 2 or more than 2 another equilibriums, so the equilibrium constant of the resultant reaction is equal to product of the equilibrium constant of the reactions which we are going to add. Therefore here Kc is equal to K1 into K2. Kc is equal to what? K1 into K2, and in the same manner K1 is equal to Kc by K2. Like this also we can take. Okay, so this is about what? Factors influencing on equilibrium constant, and one more factor, that is effect of temperature. Okay, effect of temperature and want of equation. Generally we know temperature increases, rate constant is also going to be increase, and here the effect of temperature on the equilibrium constant we can derive by using the thermodynamic relations. Okay, so here according to thermodynamics, delta G naught is equal to delta G right. See here delta G, sorry, not delta G naught, delta G is equal to delta G naught plus RT ln Q, RT ln Q. So now here in this delta G is equal to change in Gibbs free energy, change in Gibbs free energy, Gibbs free energy. Next delta G naught is equal to standard Gibbs free energy change, standard Gibbs free energy change, Gibbs free energy change, Okay, next R is the, we know R is the ideal gas constant, ideal gas constant, R is the ideal gas constant. Okay, so in this we will use the 0.0821 liter atmosphere Kelvin inverse mole inverse. This R value we use mostly in this chapter. And next T is the absolute temperature. T is what? Absolute. T is absolute temperature, and Q is the reaction quotient. So here what is the reaction quotient? So what is the reaction quotient I will explain in the next topic. Okay, simply up to that what you observe, what you remember, Q is also is equal to ratio of product concentration by reactant concentration raised to their power stoichiometric coefficient, same as the Kc, but Kc we will write at equilibrium, Qc reaction quotient we write at any extent of equilibrium, at any time of equilibrium, means before attaining equilibrium, after attaining equilibrium, and above the equilibrium also, above the equilibrium conditions also we will write. That is known as what? Reaction quotient. Okay, so these are the terms. Next here at equilibrium we know delta G is equal to 0, change in Gibbs free energy is equal to 0, but delta G naught standard Gibbs free energy is not equal to 0, and here Q will become Kc. Q will become what? K, or equilibrium constant Kc. Okay, Q is equal to K. Here K is what? Equilibrium constant. Means at equilibrium what will happen? Q will become equal to K, right? Okay. So now, and one more equation also we know, that is delta G naught. Okay, first you write delta G is equal to delta G naught plus RT ln Q, and at equilibrium we know conditions at equilibrium. At equilibrium, delta G is equal to 0, Q is equal to K, therefore 0 is equal to delta G naught plus RT ln. So instead of Q, what I will write now? What I will write instead of Q? Instead of Q I will write the K, equilibrium constant K I will write. Why? Because conditions I have taken at equilibrium. Therefore delta G naught minus, delta G naught is equal to, simply I am bringing delta G naught is equal to minus RT ln K. So, and here one more relation also is there from the thermodynamics. What is the one more relation from the thermodynamics means, children? That is delta G naught is equal to delta H naught minus T delta S naught. Okay, so here delta G naught we know standard Gibbs free energy change. Here delta H naught is the standard enthalpy change. S naught is the entropy change. Okay, delta H naught is the standard enthalpy change. Standard enthalpy. Standard enthalpy change, and delta S naught. Delta S naught is the standard entropy change. Standard entropy change. Okay, right. So now here we know, let us consider this as the equation number 1 and this as the equation number 2. Okay, so now from this equation number 1 and equation number 2, what I can write? Okay, from equation number 1 and equation number 2, so here this also delta G naught and this is also what? Delta G naught. So if LHS are equal means RHS also equal, therefore what will get here? Minus RT ln K, minus RT ln K is equal to delta H naught minus T delta S naught. So here minus sign you send that side, what will it will become? RT ln K is equal to minus delta H naught plus T delta S naught. T delta S naught. So now here instead of ln I am going to write the log base 10. So when you write the log base 10, how will you get? So here 2.303 RT log K equal to, what will you get? Minus delta H naught minus plus T delta S naught. Okay, so now log K is equal to, so you send this total terms that side, therefore minus delta H naught by 2.303 RT plus T delta S naught by 2.303 RT. Okay, so now here t will get cancel out, t will get cancel out. So now therefore it will become log k is equal to minus delta h naught by 2.303 into 1 by t. So this t I am going to separate, plus delta s naught by 2.303 r. Okay, so now this equation is just looking like what? Just looking like y is equal to mx plus c. Okay, so now when you plot a graph between the log k and t inverse of t, so how we will get the graphs? How we will get the graphs here? Okay, so now we will draw the graphs in the next page. Okay, right. See, this is clear now. So delta G is equal to delta G naught plus RT ln Q from thermodynamic relation, and delta G naught is equal to delta H naught minus T delta S naught. This is the Gibbs-Helmholtz equation. So from these two we can write minus RT ln K is equal to delta H naught minus T delta S naught. RT ln K is equal to minus delta H naught plus T delta S naught. And instead of natural logarithm, I am going to take the log values. So when I take the log values, this equation will become 2.303 RT log base 10 K and minus delta H naught plus T delta S naught. Log K is equal to minus delta H naught by 2.303 RT plus T delta S naught by 2.303 RT. So here TT will get cancelled out, delta S naught by 2.303 will remain. Okay, now I am just converting it as the log k is equal to minus delta H naught by 2.303 into 1 by t plus delta S naught by 2.303. Okay, so now here for endothermic reaction, okay, so the same reaction will do. So here how we are getting log k is equal to what? Minus delta H naught by 2.303 r into 1 by t plus delta S naught by 2.303 r. Okay, so for endothermic reactions, for endothermic reactions, what is the meaning of endothermic reaction? Heat energy is going to be absorbed by the system. If heat energy is absorbed by the system, what will happen? Delta H is positive or negative? Delta H is here will get the positive value. For endothermic reaction, delta H is equal to positive. So here positive into negative, again it will become negative only. So therefore log k is equal to minus delta H naught by 2.303 r into 1 by t plus delta S naught by 2.303 r. So now here when you plot the graph, okay, so when you plot the graph here, just it is y is equal to minus mx plus c. So here what is the y? Here we are going to take log k, and here c is the intercept on the y axis. This is the c, it is the intercept on the y axis. And how we will get the graph here? So here slope is having what? Negative value, so that constant decrease. Here we are going to take the temperature inverse or 1 by t. 1 by t is on the x axis, temperature inverse means 1 by t increases, log k value decreases, means if temperature increases, log k is also increases. Like that we can assume, or simply just assume like this only. 1 by t value increases, log k decreases. 1 by t value increases, log k decreases. And here what is the slope? Slope is equal to, here what first intercept, what is the intercept? Delta s naught by 2.303 r, and here slope is equal to minus delta h naught by 2.303 r, 2.303 r. Okay, right. Next, for exothermic reactions, exothermic reactions, for exothermic reactions, for exothermic reactions, for exothermic reactions. So for exothermic means, children, here delta H is equal to negative. Delta H is what? For exo means heat energy, heat is lost by the system. If heat lost by the system means delta H is negative. Again in this equation, minus into minus, it will become plus. So therefore, for exothermic reaction, I will get the log k is equal to delta H by 2.303 r into 1 by t plus delta s naught by 2.303 r. Okay, so now here how will get the graph now? How we will get the graph here? So here this is also log, here it is log k. Okay, it is the log k equal to log k is equal to delta h by 2.303 r into 1 by t plus delta s naught by 2.303 r. So now here log k I am going to take on the y axis, 1 by t or temperature inverse, 1 by t or temperature inverse I am going to take on the x axis. Now it is the intercept, c is the intercept. What is that c here? Delta s naught by 2.303 r. This is the intercept. Okay, let's consider here. Okay, let's consider. Okay, let's consider here. So this is the slope we are going to get here. So first intercept is what? Delta s naught by 2.303 r, and what is the slope value? So here slope is equal to delta h naught by 2.303 r. So this is the graphs related to what? Thermodynamic relation. Okay, see here we have some conditions for this one. So what are that conditions? I will explain you. For exothermic reactions, delta H is negative, so that k is what? Positive. K is greater than 1 at low temperature, k is greater than 1 at low temperatures, and all these things I will we will discuss later about these. Okay, so this is the thermodynamic relation and temperature dependence of equilibrium constant. So this is about the exothermic reactions and endothermic reactions. This is about the endothermic reactions and this is for the exothermic reactions. Here one thing we know already, that we will discuss, k is greater than 1, and k is less than 1. So these things I will explain while explaining the applications of equilibrium constant. But up to now what you remember? So what are the graphs here? How we are going to get these graphs? That part you remember. Okay, right. Next we will see applications of equilibrium constant. What are the applications of equilibrium constant? Before discussing the applications of equilibrium constant, one more simple. Equilibrium constant K independent on K independent K is independent on concentration and partial pressures. Concentration and partial pressures. How much concentration you take also, equilibrium constant for a reaction is the same at the same conditions of temperature. Okay, and also it does not depends on the partial pressures of the reactants and products. And K is independent on catalyst. K is independent on catalyst. Catalyst also cannot affect the equilibrium constant. Okay, so these are the factors which affect and which does not affect on the equilibrium constant. Now let us see the applications. What are the applications of equilibrium constant? The first one is predicting the extent of reaction. What it is? Predicting of extent of reaction. What is the meaning of predicting of extent of reaction? Means how much concentration of reactants or how much percentage of reactants are going to be converted into product, that is known as what? Predicting of extent of reaction. Say for example, we are going to take a hypothetical reaction, it is converting into B. See here how much percentage of reactant is converted into product, that is known as what? Extent of reaction. See here, if Kc value is greater than 10 cube, if Kc value is greater than 10 cube means the reaction almost completes, the reaction almost completes, only products are present, only products are present, very negligible amount of reactants are present, very negligible reactants are present. Okay, next, if Kc is less than 10 power minus 3, Kc is less than 10 power minus 3, the reaction does not at all take place. The reaction here simply you can take only products, sorry, only reactants, but not products. Okay, and one more thing here, that is if Kc is in between 10 cube to 10 power minus 3, if Kc in between 10 cube to 10 power minus 3, which means it is greater than 10 power minus 3, less than 10 cube, greater than 10 power minus 3 and less than 10 cube. So if Kc value having in between middle values means considerable reactants and products are present in the equilibrium. Considerable reactants and products, are present. Okay, next, if Kc is greater than 1 and Kc is less than 1. If Kc is greater than 1 means more percentage of reactant, more concentration of reactants and less concentration of products. If Kc is less than 1 means more it is opposite. Here Kc is greater than 1 means more concentration of product and less concentration of it is the less concentration of reactants are present if Kc is less than 1. Now if Kc is less than 1 means more concentration of reactant, less concentration of product is present. Okay, this is what extent of reaction. It is what extent of reaction. Next we'll see predicting the direction of equilibrium. So to predict the direction of equilibrium, here we are going to take one more term, that is Q. So Q is called what? Reaction quotient. What is Q here? Reaction quotient. It is the reaction quotient. Okay. So Q is equal to what here? Reaction quotient. So here what is the reaction quotient? Reaction quotient is also same like equilibrium constant only. But equilibrium constant we will take at the after existing the equilibrium. Equilibrium constant we will write at equilibrium condition only, means rate of forward reaction is equal to rate of backward reaction. In that situation only we will write the equilibrium constant. And reaction quotient, what is the meaning of reaction quotient? Means the same meaning, the concentration of products by concentration of reactants raised to their power stoichiometric coefficients only. But we can write at any stage, at a starting stage or at equilibrium state, or if you start with products, but first only we will write likewise. Simply I will write here. So A moles of A is gives rise to B moles of B in a reversible reaction. So here Kc is what? Concentration of B power B, concentration of A power A. Okay, now this is the Kc. So at equilibrium and Qc, what is the Qc here? The same expression but at any stage, of reversible reaction, Okay. So now by comparing the Qc value and Kc value, we can predict the direction of reaction. What we can do here? We can predict the direction of reaction. Means at a given condition, forward reaction is going to occur or backward reaction is going to occur, or both forward and backward reaction are occurring with equal speed. That we are going to predict. So now here simply remember Qc is less than Kc. Qc is less than Kc, which means children, the number of moles of products are very less. The number of moles of products are very less when compared at equilibrium state. Okay, so the number of moles of, or simply the concentration of product, simply you take the concentration of product, the concentration of products, the concentration of products is very less when compared to equilibrium stage, equilibrium stage. So that what will happen here, reactants are going to be converted into product. More means rate of forward reaction is more. So at this stage rate of forward reaction is more, rate of forward reaction is more. Therefore, so which reaction is favorable here means forward reaction is favorable. Okay. So here when QC means here now the equilibrium or the reversible reaction is occurring in which direction means forward direction. Okay. So reaction occur in forward direction, reaction occur in forward direction, reaction occur in forward direction, and QC is greater than Kc. QC is greater than Kc means the concentration of product, here the concentration of product is very less means concentration of reactant is more when you compared at equilibrium, and here QC is greater than Kc means the concentration of product is more, the concentration of product is more, the concentration of product, concentration of product is more, the concentration of product is more when compared to equilibrium stage, equilibrium stage. So to reach equilibrium stage, what it will do, to reach equilibrium stage the backward reaction is going to be occur. To reach equilibrium backward reaction is going to occur, backward reaction is going to occur, backward reaction is going to occur means equilibrium shifting means the reversible reaction is occurring from backward, from reactants to from products to reactants is going to occur. And we can get one condition, that is QC is equal to Kc means reaction is at equilibrium, reaction is at equilibrium, reaction is at equilibrium. Okay. So this is the direction of this is the way of predicting the direction of reaction. Okay. This is the way of predicting the direction of reaction. Okay. Next, see here only, okay. Right. And Okay, now you just consider like this. Okay, this is QC and this is the KC. So here QC is less than KC. QC is less than KC forward, and here this is the QC and KC. QC is equal to KC at equilibrium. At equilibrium, and here you consider it as the QC and this is the KC. So here QC is greater than KC, backward reaction is going to take place. Okay, so this is about the applications of equilibrium constant. Okay, so what we have discussed in this video, right? First, okay, come. Yes, what we have discussed. Right. Yes, factors influencing on the equilibrium constant. It's not coming. Okay, factors. Let us have some quick recap here. What are the factors influencing on the equilibrium constant? Stoichiometric coefficients. Means if any same chemical reaction is multiplied with a small number, that number will go to the numerator. Simply here, what I written here, K2 is equal to K1, or simply K2 is equal to 1 root over K1. Means here this reaction is multiplied with 1 by 2. That's why here root over K1 we got. And the next, see, A is gives rise to B, and means it is multiplied with a small number n. That number will goes to the numerator of original equation. Original equation is multiplied with what? A small number. That number is going to the numerator value. Some examples. Next, mode of representing the equation. Means the same reaction, first these are the reactants and this is the product. Now product is converting into react, means we are making it as the reactant is making as the product. Means new equilibrium constant is equal to inverse of old equilibrium constant. So new equilibrium constant is equal to what? Inverse of old equilibrium constant. So means when we inverse the chemical reaction, new equilibrium constant is equal to what? Inverse of the old equilibrium constant. Old equilibrium constant. Okay. Next, see some examples I have taken. Next, another one more factor, means 3 to 3 equilibriums are we are going to add, and we are going to get the new equilibrium. Means the new equilibrium is equal to product of these old equilibriums which we are added. Next, effect of temperature want half equation, we are going to derive thermodynamic relation directly. And next, delta G naught and what is the log K, graphs related to here, graphs, and here some more information is there. That information I will explain in the next videos. Okay. Next, K is independent on the concentration and partial pressure, and K is independent on the catalyst also. Next, applications. Applications what? Predicting the extent of reaction, means how much reaction is going to be complete, means what are the concentrations of reactants and products in the equilibrium stage. So that is case is greater than 10 power minus 3, means almost it is going to be complete, means only products are present, very negligible concentration of reactants, and case is less than 10 power minus 3, means only reactants, no products, means reaction not at all going to be take place. If it is in middle, means some considerable reactants and products are going to be present, and if case is greater than 1, more concentration of product, less concentration of reactant. Case is less than 1, more concentration of reactant, less concentration of product. Okay. Next, reaction predicting the direction. So which direction it is going to occur? So to know that, we are going to take one more term, that is reaction quotient. Reaction quotient Q. What is the reaction quotient? Same like equilibrium constant only, but at any stage we will write, at any stage of reversible reaction. So if QC is equal to Kc, that is the equilibrium. If QC is less than Kc, forward reaction is going to be take place, reactants are converted into product. And if QC is greater than Kc, means backward reaction is going to take only products, more products are converting into reactants. Okay, so this is about the applications and applications of equilibrium constant. Okay, right. Okay, so now finally, thank you for watching. Thank you for watching. Right.